Chapter 6, Section 7, we talk about the imaginary number I, and this gets us ready for the Algebra 2 standard number 6, where we add, subtract, multiply, and divide complex numbers. And you might need to know why we need I in solving equations. You'll need to know the definition of a number I. You'll need to know how to rewrite the square root of a negative number in the equivalent form using I. And you'll be able to use I to simplify square roots of negative numbers. And where all this came about is throughout history, mathematicians have developed new numbers as they need to solve equations that they weren't able to solve before. So in solving x plus 3 equals 2, we needed negative numbers to solve that. In solving equations like x squared equals 2, and you square root both sides, you get the square root of 2. Well, we weren't able to do that until we developed irrational numbers. So we need a new number system to solve an equation that looks as simple as this one. X squared plus 1 equals 0. We cannot solve that over the set of real numbers. So what we need to do is to solve this equation, we would subtract 1 from both sides. We would take the square root of both sides. And again, taking the square root of negative 1, we ask the question, what number times itself equals negative 1? And in the real number systems, there is no solution to that equation. What number times itself is negative 1? There is no number times itself in the real number system that equals negative 1. So what we've had to do is we've had to define a new number system, which is called the imaginary numbers. Imaginary numbers consist of all numbers in the form bi, where b is a real number and I represents a new number, the imaginary unit. Remember that we called 1 the unit when we talked about counting numbers. I is the imaginary unit, and I squared is equal to negative 1, and I represents this quantity, the square root of negative 1, which does not exist in real numbers, but will now exist in imaginary numbers as the imaginary unit I. So in the situation, if we have the square root of a negative number, we're going to factor out the square root of negative 1 and convert that to I, the imaginary number, and then have the square root of that rest of the radicand itself. So our strategy is to factor out that square root of negative 1, replace it with I. So let's look at a numerical example of that. According to our strategy here in green and our property here in blue, square root of negative 5, we're going to factor that out as the square root of negative 1 times the square root of 5 using our product property of radicals. And then the square root of negative 1, we're going to replace that with I. Square root of 5 cannot be simplified any further, so the square root of negative 5 in the imaginary number system is written as I times the square root of 5. So for the square root of negative 25, we're going to factor out the square root of negative 1. We're going to replace that square root of negative 1 with I. Square root of 25 is 5. Now, in this example, we wrote the I first. In this example, we wrote the I last. Typically, we write the I last. However, I wanted to make sure in this example 1a that you didn't think the I was still under the radical sign. So sometimes I will write the I before the radical so we don't get confused. In our next example, the square root of negative 50, well, let's factor out the square root of negative 1. Looking for perfect squares, we'll factor out the square root of 25, and we'll be left with our irrational square root of 2. And that simplifies. The square root of 25 is 5. The square root of negative 1 doesn't exist in the real numbers, but it does exist as the imaginary unit I, and then times the square root of 2, and that's our simplified answer. It does take a while to get used to this kind of thing. Before you can add or subtract, first of all, you're trying to add or subtract things that don't exist. So we have to convert them into imaginary numbers where they will exist. So again, factor out the square root of negative 1 from the square root of negative 16. Factor out the square root of negative 1 from the square root of 49. Replace each of those square roots of negative 1 with I. And then the square root of 16 is 4. Square root of 49 is 7. And I is not a variable, but when we're simplifying just as if it were a variable, 4i minus 7i is equal to 3i. And that's our simplified answer. Likewise here, we can only add radicals if they have the same root index, same radicand, which they do. And then we have I, and we have another I. One of those, I square roots of 2, plus 3 of those I square roots of 2, is 4 of those I square roots of 2. Multiplying, we cannot multiply them until we convert them into something that does exist. Square root of negative 4 does not exist in the real number system, neither does the square root of negative 25. So a mistake alert here is to make sure you convert them into something that does exist, like the imaginary numbers, first before you multiply them. So factor out the square root of negative 1 and then the square root of 4. Factor out the square root of negative 1 and then the square root of 25. The square roots of negative 1s now, replace those with I, which does exist in the imaginary number system. And then the square root of 4 is 2, square root of 25 is 5. And when we multiply, 2 times 5 is 10, I times I is I squared. Now in our previous definition we said I squared is the same as negative 1. So we're going to replace I squared with negative 1. 10 times negative 1 is negative 10. And that's our simplified answer for example 3a. Now, here's the mistake alert. Make sure you convert them to imaginary numbers before you multiply. Students sometimes forget to do that, and here's what you end up with. You think that you can multiply them, but you can't. But students will say, well, that's the same as the square root of 100, which it's not. The square root of 100 is 10. Well, that's true. But obviously our answer was negative 10, not positive 10. So do not multiply the square root of negative 4 times the square root of negative 25. They don't exist. Their value is not existent. What we need to do is convert them into imaginary numbers where we do have a value, and then we can multiply and simplify. So be careful to make sure you factor out all your square roots at negative 1 first. Alright, example 3b, we've got the square root of 2 times the square root of 3. We can multiply that to get the square root of 6. I times I is I squared. Remember again that I squared was defined as negative 1. So that's negative 1 times the square root of 6. Well, if I represents the square root of negative 1, and we couldn't have a square root in the denominator of a fraction, then we can't have an I in the denominator of a fraction either. So we're going to multiply both the numerator and denominator by I, remembering that I squared will become negative 1, and that takes care of the radicals. In the numerator we have 2i, in the denominator when we multiply 3i squared. Remember I squared is negative 1, negative 1 times 3 is negative 3, and we don't like to leave negatives in the denominator of a fraction. So if you multiply both the numerator and denominator by negative 1, we get negative 2i over 3, our answer in simplified form. Alright, let's check into this next example, 4b. We cannot leave the square root of negative 2 in the denominator. So let's factor out the square root of negative 1 and rewrite that as I. And then we have the square root of 2. And we can't leave I or a radical in the denominator. So the 1 we're going to multiply incorporates an I. To get rid of the I, we get I times I is I squared, there's negative 1. And then the square root of 2 to rationalize the denominator. In the numerator, that gives us 6i square root of 2. In the denominator, the square root of 2 times the square root of 2 is 2. I times I is I squared. Again, I squared is negative 1. Negative 1 times 2 is negative 2. And we can simplify here and reduce factors. 6 divided by negative 2 is negative 3 times I times the square root of 2. And that's our answer in simplest form. Again, we can't add or subtract until we first convert non-existent real numbers into imaginary numbers. So let's do that in this example. Factor out the square root of negative 1, and then we've got the square root of 9, square root of x squared. Factor out the square root of negative 1, factor out the square root of x squared. Square root of negative 1 is I, square root of 9 is 3, square root of x squared is x. Square root of negative 1 is I, square root of x squared is x. We do have like terms here. We've got 1ix plus 3 more ix. Since they're like terms, we can add them to get 4ix. Again, don't multiply till you convert them to imaginary numbers. So factor out the square root of -1. Remember, the square root of -1 is the same as the imaginary unit I. We can multiply the i's now. I times I is I squared. Square root of 6y times the square root of 2y is the square root of 12y squared. And we've got to simplify the i's on our perfect square factors. So 12 is a perfect square factor of 4 and a non-perfect square factor of 3. Y squared is a perfect square. I squared is -1. Square root of 4 is 2. Square root of y squared is the absolute value of y. And the square root of 3 times -1 gives us -2 times the absolute value of y times the square root of 3. That's our answer in simplified form. To solve some equations, let's move to that now that we've added, subtracted, multiplied, and divided imaginary numbers. Subtract 19 from both sides. Divide both sides of the equation by 2. Take the square root of both sides. The square root of x squared is the absolute value of x. And let's factor out the square root of -1. And then 8 has a perfect square factor of 4, a non-perfect square factor of 2. The square root of -1 is I. The square root of 4 is 2. The square root of 2 won't simplify. And remember that this is the absolute value, so we have to consider the positive 0 case and the negative case. And remember, when that was equal, we had a little shortcut we learned earlier in the year that plus or minus 2i square root of 2 is my answer for that particular equation. Again, it's x squared, so the fundamental theorem of algebra says we're looking for two solutions. Positive 2i square root of 2 is one, negative 2i square root of 2 is the other. Alright, what we need to know a little bit more about I in this particular case is when we take I and then square it and then cube it and then raise it to the 4th power. Remember, the imaginary unit I represents the square root of -1. By definition, I squared was -1. I cubed is the same as -I, and I to the 4th power is the same as 1. And it turns out this pattern repeats over and over and over in a little what I call icicle, which is why that looks like an icicle there. So we're replacing the square root of -1 with I. I squared is the same as -1. I cubed is the same as -I. I to the 4th is the same as positive 1. I to the 5th is the same as I to the 1st. I to the 6th is the same as I squared, which is -1. I to the 7th is the same as I cubed, which is the same as -I. And then I to the 8th is the same as I to the 4th, which is the same as positive 1. And this pattern repeats over and over and over again, which is why I wrote etc. It's a cycle of i's. So let's simplify I to the 10th. And rather than going round and round and round the merry-go-round, we know that there's only 4 particular choices. So what I suggest we do is we take the exponent 10 divided by 4, throw away the quotient 2, and keep our eye on the remainder 2. And that says that I to the 10th is equivalent to I squared. And remember that I squared is the same as -1. So I to the 10th is the same as -1. This process of dividing and ignoring the quotient but paying attention to the remainder is called modular arithmetic, which is sometimes called clock arithmetic. Let's look at I to the 27th then. Take 27 divided by the 4 choices, throw away the quotient 6, keep the remainder 3. That means that I to the 27th is the same as I to the 3rd power, which from our little icicle and definition we said is the same as -I. Well, what if we go I to the 124th power? Rather than going around and around and around that icicle, let's take the exponent 124 divided by 4, throw away the quotient 31, look at the remainder 0, and that means that I to the 124th is the same as I to the 4th power, or just 1. And when we do this process, again, dividing two integers, we ignore the quotient, we look at the remainder. That's called modular arithmetic or clock arithmetic. The remainder is called the modulus. So think about how you tell time, not military time, but in a clock we've got 12 hours in the cycle, And after 12 o'clock, we don't say 13 o'clock. We go over again and say 1 o'clock. 2 hours after noon, we don't say 14 o'clock. It's 2 o'clock. So the powers of I, there are 4 choices, and we would divide by 4 and look at the remainder to find out how to simplify our power of I. Well, that's our look at imaginary numbers and our new number system. It's important that you know how to do that.